Let's say I have some pure water and I dissolve some solute into that water. And I place this water into some kind of apparatus, this U-shaped glass tube. And what I will make a note of is that if I allow this system to equilibrate, the side with more salt in it will have a higher level than the side that doesn't. And this is an interesting phenomenon if you haven't seen it before, and the reason that we see this is due to osmotic pressure. And so what I'm going to do in this video is introduce osmotic pressure and work through an example problem. And so the fundamental intuition behind osmotic pressure is that there is a chemical potential or a concentration gradient that water wants to equilibrate. And what that means is that water wants to move from areas of low concentration to areas of high concentration. And it has to do partially with entropy and maximizing the number of possible microstates available to a system. And what I mean by that is if I had in a flask, for instance, a super highly concentrated drop of solute, and I place that into the solution, over time the solute's going to mix throughout the solution and we're going to get an equilibrium because the water will want to solvate as much of that solute as it possibly can in order to reach a homogeneous, uniform, lower concentration overall. And if you want to know more about the intuition, you can take a statistical mechanics course, but for the sake of an introduction in chemistry, this will suffice. And so for an example problem, let's say that I added 10 grams of salt, NaCl, into 490 milliliters of water, and I want to know what is the osmotic pressure. And a way that you can visualize what is going on here is, let's say I add the salt to the right half of this apparatus here, and the left half is just going to contain the water, the pure water. And I have these two halves separated by a semi-permeable membrane. And what this semi-permeable membrane refers to is the fact that only water can pass, not the ions. And this is very important because if the ions could pass through it, the ions would just go right through the membrane and there'd be no osmotic pressure. But because only water can pass through this membrane, what will happen as time evolves is we're going to see a decrease in the left half because water is going to be moving from the area of low concentration to the area of high concentration, and consequently there will be an elevation in the right half of the water level in our apparatus. Now, to determine how much pressure I will need to exert on this system, so if this was a closed system, if I capped this system off, how much pressure do I need to apply to this region 1 here in order to maintain a constant level between these 2 points? That pressure that needs to exist within this region 1 or volume 1 is what the osmotic pressure is, and that is denoted by the variable called pi. And the key equation that we're going to come to time and again for osmotic pressure is pi equals I CRT. I is the Van 't Hoff factor. I tells us the number of ions after dissolving a solute. And so for the case of salt, because we have NaCl going to Na plus Cl minus, I equals 2 because we have 2 ions that exist. Now, when you look at things like glucose, if you're dissolving a glucose molecule into water, I is going to be equal to 1 because glucose isn't dissociating into anything else. But for this example, because we're working with a salt that has 2 ions that get generated from dissolving it, I will be 2. Okay, so now that we've established what I is, our next task will be determining what the concentration C will be. And for the sake of this example, I will assume that 10 grams of sodium when dissolved in water is going to be equivalent to 10 milliliters. So the volume of our solution after I've added 10 grams of salt will be 500 milliliters, which is equivalent to 0.5 liters. And the moles of solute, the moles of NaCl, will be equivalent to 10 grams divided by the molecular weight, which is 58.4 grams per mole. And this will be equal to 0.17 moles. And I encourage you to do the algebra on your own. But to continue, now that we have the volume of solution as well as the moles of solute, we will note how molarity, C, is equivalent to, in this case, we're going to have 0.17 moles divided by 0.5 liters. This will be equal to 0.34 molarity, moles per liter. Okay, and now that we've established C, we'll make a note how we're always going to know what R is, because R is the ideal gas constant. R is equal to 8.314 liters per liters times kilopascals per mole per Kelvin. And then the temperature, this is a key variable here. We have to make sure that temperature will have units of Kelvin. And so because we're given units in 25 degrees C, temperature in Kelvin will be equal to 25 plus 273, which in this case will be 298 Kelvin. Okay, so now that we've defined all of the variables we need, we can establish what pi will be, what our osmotic pressure is. And so plugging this into the equation, what we eventually find is that pi must be equal to 1680 kilopascals. So I need to apply 1680 kilopascals of pressure to side 1 here in order to maintain a constant level of water in this apparatus. And so this is going to wrap things up for this introduction and example to osmotic pressure. I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.